Alright, today we're going to talk about molecular geometry, which is pretty much going to have to do with the fact of determining what shapes. So what I'm going to do is take you through the PowerPoint. It's going to have all the different options. Then I'll show you a chart at the very end that I'll give you a copy of in class to help us solve these problems. Okay, the molecular geometry is governed by what's called the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. And this is the idea that electron pairs will orient themselves in order to minimize repulsive forces, but they also will get as far away from each other as possible, and that's the repulsion piece. So any of these electron pairs will get them as far away apart from each other. So if this is a bond, okay, two bonds coming off of that central group, they're on opposite sides. Now we're going to talk about how many bonding groups, how many lone pairs, and also the bond angle. And if you think all the way back to your protractor, if we looked at the angle between this bond and this bond, this would be 180 degrees. And so we're going to look at the bond angles, and then we'll do some 3D stuff in class. Okay, there are two types of bonding pairs, and if you think back to Lewis structures, right, this kind of goes hand in hand with those. You have bonding pairs or bonding groups, and you have lone pairs that are non-bonding electrons, and those are the ones that we wrote on the top of the Lewis structure like this. Now, lone pairs will repel more strongly than bonding pairs. It means that they will push everything further away, hence valence shell electron pair. That's what I always think of. But those bonding pairs will push them away more strongly. And when we're talking about bonding groups coming off of a central atom, double and triple bonds are only going to count as one, and you'll see that come into play a little bit later. Okay, so for VSEPR theory, the lone pairs will reduce the bond angle between atoms. Again, the bond angle would be kind of this imaginary line where we could measure the angle between the kind of imaginary lines that these bonds would make. And there, for each shape, you're going to have to know the bond angle and what that corresponds to. Now, here are the steps. You draw the Lewis dot structure, or the Lewis diagram, which we've been doing. We then tally up how many types of electron pairs are on that central atom. Double and triple bonds will only count as one bonding group when it comes to geometry. And the shape is determined by how many bonding pairs, as well as how many lone pairs. And that's what's going to determine what shape it falls into. And again, those 8 common shapes and their bond angles, you should have received a chart in class. And I'll show this to you at the end, and these you do have to just memorize. Okay, so we got to get out the little flashcards. There is a Quizlet set up for molecular geometry, so you can use that as well. All right, so to start off with, if you have two total groups coming off of the center, they're both bonding groups. This is going to be what we refer to as linear and 180 degrees. And so if you have in the center here, you've got two bonding groups and no lone pairs, it's automatically going to be linear. Now, one thing that diatomic molecules, any diatomic molecule, or anything that's only made of 2 atoms, will also always be linear. Okay, will always be linear. It's just one of those. All right, now if it has 3 total groups coming off of it, and they're all bonding groups, okay, this one is going to be what's called trigonal planar. And again, when you see the 3D versions of these in class, I think they make a little bit more sense. But trigonal planar, there are 3 all in the same plane. And if you divide that circle up into 3 parts and pieces, you get 180 degrees. Okay, so the bond angle here is going to be 120 degrees, which will get you the angle between each of these bonds. And an example of that is boron trifluoride, because boron only needs 6 electrons or 3 bonding groups to be happy, so it's an exception. Okay, now if you've got 3 total, 2 bonding and 1 lone, every time you see one of these little balloons, it represents an electron cloud. And so you're going to see me draw these little dots. It's kind of another orbital. It's another end of the p orbital, or where electrons can be floating around. I like to draw the 2 dots because that's how we draw it on the Lewis structure. They start to look like aliens here pretty quick. This is bent, and the angle is less than 120. Okay, if you had one where, let me bring up the sample here, but if we had one from the last slide where they were all bonding groups and it was 120, essentially what happens is if you get rid of one of those bonding groups and you replace it with a lone pair, all right, it's going to push those bonds together so that the bond angle is now going to be less than 120 degrees. Okay, 4 total. 4 bonding and no lone pairs. It's going to be what we refer to as tetrahedral. Now you might think it's going to form this like 2D cross because that's the way that we draw it when we do our Lewis dot structures. However, the reality is if you look at it in a 3D space, each bond angle is going to be a 109.5. And we'll look at this in class to kind of make sure that we can compare this, but this one's going to be 109.5. And this is going to, methane is an example where you have a central carbon and 4 hydrogens coming off of it. Okay, now here's another one with 4 total. You've got 3 bonding groups and 1 lone pair. So again, this one really looks like the alien, but here's the lone pair that's up here. I drew them in there. And what this lone pair is going to do is it's going to push them all closer together. So it's going to reduce the bond angle from 109.5 to 107. And ammonia is an example of this because ammonia has 3 hydrogens coming off it and it still has a lone pair that we typically draw on top in addition to the 3 covalent bonds. Okay, still with 4. Now we've got 4 total groups, 2 bonds, right? There are bonding groups, and 2 lone pairs. Okay, so you'll see this kind of represents that these suckers get as far away from each other as possible. Now we've got the 2-headed alien. The name of this one is also bent, but this time the bond angle is 104.5, so it has a different bond angle than when we had 2 bonding groups and 1 lone pair. And water is a really common example of this because the oxygen has 2 extra lone pairs up top there. Okay, now sometimes we get more than 8 in the octet, and we saw this a few times in some of our Lewis structures, but if you have 5 total all coming off the center and they're all bonding groups, it's what we're going to refer to as trigonal bipyramidal. And essentially where that comes from, they have 2 bond angles, 120 and 90. The 3 in this plane have a bond angle of 120, and then these guys have a bond angle of 90 degrees. So you kind of have 3 that are all in one plane. That's where the trigonal comes from. Bipyramidal is that if you filled in all the sides to this, you'd have 2 pyramids kind of stacked on top of one another. And a common example of this is going to be phosphorus pentachloride. Okay, phosphorus pentachloride. Then last but not least, if you have 6 bonding groups, all lone pairs, this is going to be what we refer to as octahedral. You kind of have 4 that do form this T right in the middle and then 2 sticking straight up. And if you were to fill in all the sides of this, you'd end up with an 8-sided cube. That's where the octahedral comes from. The bond angle is 90 for all of these because they're all going to be 90 degrees. And an example of this would be sulfur hexafluoride. Okay, sulfur hexafluoride. So, for example, if I have what we would get, a question might say, draw the Lewis dot structure and then name the geometry. This one I'm giving you the Lewis dot structure. So when we look at this, we're looking at the central atom. Sometimes there's more than one central atom, but for most of them, it's a central atom. And if we look at phosphorus, you have 3 bonding groups and 1 lone pair. So if you go to your chart, you're going to find out that that's going to be trigonal pyramidal with a bond angle of 107. Okay? And that's just what the 3D structure would look like, where they're actually kind of all pointing down a little bit, and then our lone pair would be up here. All right, carbon dioxide. If you look at that central carbon, whenever I like to do these on paper, I like to highlight that middle atom. It just helps me visualize and kind of focus on what I'm trying to answer. But if I look at that central carbon, there's 2 groups, both bonding groups, which is going to put it in linear, and the bond angle will be 180 degrees. And even though they're double bonds, each one only counts as 1 bonding group coming off of that central carbon. And like I mentioned before, you have to be familiar with the information on the chart, which is, nope, I don't want that, which is going to be this. Okay, you got this summary chart the other day in school, and it kind of puts it all, let me get it so that we can see it all here, so that it's all in one place. But here's the number of bonding groups, the number of lone pairs, the name of the geometry, and then the bond angle. And again, this is stuff that you have to have memorized. Some of it will be a little bit more common than others based after we do the activities, but we do have to have these memorized for the test and for the final exam. Okay.